Good morning. My name is Rebecca Clark-Bash, and I'm going to be talking to you this morning on instrumentation, filters, analog to digital conversion, and math. If you have any questions about this presentation, or if I refer to any additional handouts that might be helpful to you regarding this content, please feel free to email me at opcal@aol.com. This entire presentation will be in your Dropbox folder. My background, I started in EEG. I went to an EEG school in Wisconsin a long time ago, I think 1921 or something. Feels like it, feels like that long ago. But I'm registered in EEG, EP, CNIM, and CLTM. I'm also a fellow of the FASNM and a fellow of FASET. I was the first technician on the FASNM board, and I was also the first technician to be awarded fellowship status of the FASNM. I really love teaching, and I'm sorry I couldn't be with you in person to share your questions and share your interest. So the first document that I want to reference, and this is available free at acns.org. That's Apple, Cat, Sam, Mary, ACNS. I'm not really firing on all cylinders this morning. ACNS, the American Clinical Neurophysiology Society, ncns.org, on their website, free. If you go to that website, look at the left-hand margin, and you will see an option called guidelines. And you can go ahead and access those guidelines, and the digital requirements are in that guideline. Now I'm going to talk about all the important features of that guideline during my lecture today, but if you'd like to read the full article, just go to acns.org. So we don't really have brain waves. We have brain activity, we have neurophysiologic activity, but there's a process in taking that activity and converting it into a waveform. So data quality, how much does the EEG waveform look or replicate what's really happening in the brain? That depends on your amplifier settings and your A to D conversion settings. So the definition of analog to digital conversion is the method by which your instruments convert the continuous voltage change of the recording into a sequence of numbers, or digital recording. There are two characteristics of A to D conversion, two quality factors. One is horizontal resolution. That impacts our frequency resolution, and then vertical resolution impacts our amplitude resolution. Well, we're going to start today with horizontal resolution. On your instrument, you have a choice of sampling rates of 256, 512, or 1024. And with many things, we always think bigger is better, more is better, but that may not necessarily be true. So if we were to ask which of these three would best serve to give us beautiful EEG, you might be tempted to pick 1024, but we don't really want to pick a bigger number if we don't need it, because not only will it resolve brain waves, but it's also going to resolve noise. So we want to get a well-represented EEG. We don't want noise resolution. So how many sampling points are necessary? How do I know? How do I figure that out? So in order to figure out the necessary number of sampling points, we need to know the frequency of the signal being recorded and the length of the recording. Now, everything in EEG is defined by the number of times it happens in a second. So our length, when we're calculating sampling rate, is 1 second. Now, the frequency of the signal being recorded, we are recording with filter settings between 1 and 70 hertz. So we're looking at activity between 1 and 70 hertz. And in deciding what sampling rate is optimal, you have to look at the fastest event that you're recording. and in EEG, it's 70 Hertz. The high filter setting defines and is equal to the fastest frequency being recorded. So we're going to use the example of the star when we're talking about horizontal resolution. Remember, horizontal resolution impacts frequency, impacts the number of peaks. This is a 5-peak star. Let's say this is a 5 Hertz star. And if I were to look at this and say, what is the fewest number of dots? What is the fewest number of sampling points I would need to recreate this star? You might say 5. It's a 5 Hertz star, 5 peak star. Let's try using 5 sampling points to recreate it. And when we do that, our end result doesn't look anything like a star at all. What we really need is we need a sampling point for every peak and every trough, every up, every down. So if this is a 5-peak star, a 5 Hertz star, this picture simplifies the fact that in order to get this star to look the same as a 5-point star, after we've digitized it, we need a minimum of 10 sampling points. So for any frequency, 5 Hertz, we need twice the number of sampling points, one for every peak, one for every trough, in order to see all of the frequencies that we're collecting. So if we have a 5 Hertz waveform, we need at least 10 sampling points. In EEG, or high filters at 70 Hertz, we need at least 140 sampling points. This rule, this principle, this theorem is Nyquist. It says that the sampling rate should be at least twice as fast as the fastest frequency being recorded. So again, in EEG, we're recording a high filter of 70 Hertz. The fastest activity we look at is 70 Hertz. So we need at least 140 sampling points. Now, if you're taking the ABRT exam, be careful about the language of the question. In a board exam, they might ask for the optimal, or they might ask for the minimum. So Nyquist says you have to have at least 2 times. ACNS says you have to have optimally 3 times the fastest frequency. So if they are asking you what is the minimum, what is Nyquist, we're recording with a high filter of 70 Hertz, you have to have at least 140 sampling points. If they are saying what is the optimal, optimal is 3 times. And in fact, again, look for the words optimal and minimum. In the latest digital media guideline, they say that the sampling rate should be at least 256 samples per second. If we don't follow that rule, you will have a digitization-induced artifact. It's a result of inadequate sampling rate where we're not using at least 2 times the maximum frequency being resolved. You're going to get aliasing. Aliasing distorts frequency. So on a board exam, they might use a definition like this. Aliasing, by definition, is a phenomenon of fast frequency components of an artifact or signal showing up on the EEG as a slower frequency. So a good sample question might read something like this. Aliasing is an artifact causing corruption of, and of course, the answer is C, frequency. The formula for sampling rate is the one you see here. I'm going to give you, I don't really like the way this is written. I'm going to give it to you in a little bit different presentation, a little bit different way to represent it. Now, when we look at our EEG on our screen, it's not dotty. It's not a bunch of little dots on our screen. It's a solid line, because what the computer does is after it digitizes it to specific data points, it connects the dots. The data in between each sampling point, the data in between, I think I just made that word up. in between each. No, the time in between each dot is called, each sampling point is called the dwell time or inter-sample interval. Those are synonymous terms. Now, the interval has an inverse relationship to the sampling rate. So in this first example here, when we have more frequent sampling points, we have a shorter inter-sample interval. When we have less sampling points, you increase the inter-sample interval or dwell time. So they have an inverse relationship to one another. Now, in this formula, if on the Abbott exam, you might be asked to calculate the number of sampling points given a dwell time, or the dwell time given, or sampling points given a specific dwell time. So if the answer choices are in milliseconds, you're going to divide, if given sampling points, you're going to take 1,000 divided by sampling points. If, however, they give you dwell time, you're going to take 1,000 divided by dwell time to achieve your sampling. So if the answers are in milliseconds, you're going to use 1,000. If the answer is in seconds, you're going to use 1 divided by sampling to get dwell, and 1 divided by dwell to get sampling. So written out in a formal format, you have 1,000 if they give you sampling points, and you are expected to calculate dwell. You take 1,000 divided by the sampling points. That gives you the dwell time in milliseconds. If they give you the sampling points and your answer is in seconds, you take 1 divided by the sampling point. To calculate sampling points, you take 1,000 divided by dwell time. Time will always be entered into the calculator first. If you use sampling points divided by time, there could be an answer exactly that number, and you're going to think, yeah, I got it right, there's the number, but it's going to be incorrect. So time is always entered into the calculator first, and on the Prometric software, there will be a calculator available to you for questions that require one. Pay attention to units. The choices on the Abbott exam may have the exact same number, but different units. So you might be asked to calculate sampling rate, and ABCD, every choice is 256, yet the units is different. So sampling rate is in hertz, also samples per second, but pay attention as you're memorizing formulas. Unit of measure. What's the unit? So I have some sample questions laid out for you here in your handout, and I also have the answers, which I'll show you in a minute. But if they're asking you, if you have a sampling rate of 256, what is dwell time in milliseconds? You will take 1,000 divided by sampling rate to derive your answer. If they give you the answer in seconds, you're going to take 1 divided by the sampling rate to get your answer. So in your handout on Dropbox, I've provided all the correct answers to these questions, so you can practice calculating them. And if you're going to take your Abbott exam, they do give you 2 pieces of paper, scratch paper, and I do recommend that one of the things you write down when you come in the room, one of the things you should write down are your formulas. So here are some examples of what kinds of questions you might encounter on the test. So here it says, what is the minimum dwell time? What is the minimum intersample interval with a sampling rate of 256? Or they might have a different number in milliseconds. So you just take the time in milliseconds divided by the sampling rate in hertz, and in this example, 1,000 divided by 256 equals 3.91. Or they could ask you, instead of giving you, of course, they're not going to give you just one choice. They might have the same number in different units. So pay attention to what is the answer unit. And in this example, I've also put down what would happen if you were to do the division wrong. Instead of 1,000 divided by 256, if you accidentally said 256 divided by 1,000, it's going to give you 0.256 milliseconds, which is most likely going to be one of the choices, and it's a wrong choice. Here's another sample question, same question. What is the minimum dwell time? What is the minimum intersample interval with a sampling rate of 256? So the correct answer in this question, because it is in seconds, that's correct answer. This is the correct answer, wrong unit, and if we did it entirely incorrect. So again, that's the formula for calculating dwell time / intersample interval. Those terms are synonymous. That would allow you to calculate what the dwell time is. In this problem, they can also give you the dwell time and ask you to calculate the sampling rate. So again, it's just 1,000 divided by dwell time, and there are your answers. Now, another type of question they might ask you is they might provide for you the frequency of an EEG waveform. I didn't give you a formula that has one of the variables, the frequency of the waveform. So I gave you a formula that had one of two variables, either sampling rate or dwell time. So in this question, the first thing I have to calculate is, if my waveform is 5 Hertz, my sampling rate has to be at least twice that, or 10. And then I can go back to my math, 1,000 divided by 10, or if it's in seconds, 1 divided by 10. And here are the answers for that. So another way to write that question out is, what is the minimum dwell time or intersample interval for a 5 Hertz, or they could say any other number, EEG waveform. So in this question, they don't provide the sampling, which is the only variable I gave you to calculate dwell time. So in order to obtain an appropriate sampling rate, you have to double the EEG waveform frequency. So if it's a 5 Hertz waveform multiplied by 2, that's 10 Hertz. We meet Nyquist. And then you're going to take 1,000 divided by 10, or if it's in seconds, 1 divided by 10. So what is the minimum dwell time intersample interval for a 5 Hertz EEG waveform? Correct answer is 100 milliseconds. They might also have 0.1 milliseconds. That's the wrong unit. And also be sure time goes into the calculator first. There's a feature on EEG machines called sample and hold technology. It's the best digitization method. If you don't have sample and hold technology, but rather are using sequential sampling, you're going to introduce sampling skew, where the first channel and the last channel aren't time synced, which could make a spike look like it's not phase reversing at the same time. On digital EEG systems, your calibration occurs when you enter the EEG program. And on digital EEG machines, baseline is established, and that is the point at which all amplitude measurements are taken. Now, you don't have to proactively do anything to make that happen, but that is true system calibration. Now, in the candidate handbook, it talks about metric conversions. And they're not going to ask you how many microvolts in a volt, how many milliseconds in a second, but your math is going to be necessary. Your metric conversion is going to be necessary to do those problems that we just talked about. Horizontal resolution defines frequency. Vertical resolution defines amplitude. So vertical resolution is dependent on the size of the A to D converter, and you can't change that. You can't go into your equipment, into a settings file, and change the size of your A to D converter. It is what it is, like buying a 4-door car. You can't go back to your dealership and say, hey, I'd like 8 doors on this car. It isn't possible. So the size of the A to D converter is not configurable. What you can edit, change, enhance is your amplifier sensitivity. Now for the A to D converter size, the 16-bit is minimum. Most EEG systems are 24-bit. And what does that mean? It doesn't matter. On the Albert exam, they're not going to ask you anything beyond that. When you talk about the bit size of the A to D converter, it defines the number of unique voltage values or steps that you would have available to you if your A to D converter size was 8-bit or 9-bit. And in order to calculate the number of unique voltage values, you take 2 to the power of the bit size. So if it's an 8-bit A to D converter, you take 2 to the 8th, and that gives you 256 steps. There are 8 bits in 1 byte. If you over amplify your data, you will have waveform clipping. Waveform clipping is this squaring off of the waveform. Sensitivity of your instrument is defined in microvolts per millimeter. And with sensitivity, you know, the smaller number makes bigger data, a bigger number makes smaller data. If you're going to select the most sensitive sensitivity setting, then number 1, if you have questions like this on your exam, the answer is always in microvolts per millimeter. So the biggest number is least sensitive, as we see here, 20 microvolts per millimeter, and the smallest number is most sensitive, 5 microvolts per millimeter. You should, for the Albert exam, you should know the definitions of gain and sensitivity. Gain is the ratio of signal voltage obtained, blah, blah, blah. This is too hard for me to memorize. So I just remember that in gain and sensitivity have a similar definition, but in the definition of gain, output is over input, and sensitivity, input is over output. So the way I remember this is if I gain weight, I'm overweight, so output comes first in the definition of gain. So recording gain must be set to match the vertical resolution of the A to D converter for the most effective signal resolution. That's important to know for the exam. So again, the smallest number, the better vertical resolution. And again, remember, it's always in microvolts per millimeter, not millivolts per millimeter. Vertical resolution is improved by increasing the sensitivity. Every channel that we look at is the difference in activity between 2 electrodes. So in this example, input 1 is 10 microvolts, input 2 is a minus 40 microvolts. Now, on the Albert exam, they may give you a question like this. They will give you the voltage values for each electrode, and know that if you're calculating the output, you have to subtract those. And in this question, the second number being negative, when you have 2 negatives in a row, you have to add those together. So if I had 10 microvolts minus a minus 40 microvolts, that's going to end up in a 50 microvolt positive response. Common mode rejection, the reason that we use differential amplification, the reason we take 2 different electrodes and subtract them is you get rid of any common noise, like 60 cycle. So it's based on the premise that you have to have low impedance. So this common mode rejection only works if you have low and balanced impedance. So it's better if you had 2 electrodes at 8 k ohms than it is if one was at 0.1 and one was at 5, even though they both meet that criteria. Now, in an older guideline, it stated that the minimum common mode rejection ratio should be 10,000 to 1 or 80 dB. In the new digital guideline, it states the minimum is now 90 dB. The common mode rejection, if it were set at 120 dB, it's 1,000,000 to 1. And the primary artifacts that are gotten rid of with this ratio are 60 hertz and radio frequency noise. The key factor in getting rid of artifacts is electrode impedance balance. With common mode rejection, rejection is based on, so right now, all of you are probably guessing what the answer is, but I'll tell you what happens in my classroom 100% of the time with this question. People will guess amplitude, then people will guess frequency, but the answer is neither. It is cycle. Cycle is defined as these two waveforms having exactly the same amplitude, exactly the same frequency, and exactly the same, what they might call phase or polarity. And again, they cancel out physiologic, which are biologic artifacts. Those are artifacts coming from the patient, like EKG and respiration, or non-physiologic, which would be things from equipment in the area, like the respirator or an electric bed. Cancellation occurs when both electrodes in the pair are equal. If you have electrolyte gel or salt jelly between two electrodes, that would be using things like 1020. If it's smeared between two electrodes, you're going to get a flat line. Salt bridges will never cause 60 cycle artifact. When you have a salt bridge, your impedances are less than 100 ohms. Summation occurs when two outputs of opposite polarity are subtracted during the differential amplification process. As in this example, where input 1 is -70, input 2 is +85, and you get this huge, very similar in numeric value, but opposite sign, causing summation with this huge output. In the guidelines, it says the electrical impedance of the amplifier should be 100 megohms or more. So when we talked earlier about any numeric value that you memorize for the exam, yes, memorize the number. Yes, memorize the unit, but also memorize the reference value, because you might have a equal to or greater than 100 megohm choice, or less than or equal to 100 megohm. So it is, the answer is greater than or equal to 100 megohms. Of course, each channel has 2 electrode inputs into it. Filters function to exclude activity that isn't relevant to the diagnosis interpretation. So there's a low filter and a high filter. Digital filters don't cause phase shift, and we're going to talk about phase shift in just a second. Passive RC filter, that might come up on the exam, never the answer to anything. The high frequency filter is called a low pass filter, because the high frequency filter, think about him as police, and a bunch of frequencies are coming in the door, and he's saying, I don't care anything about the low frequencies, you pass by me. I'm only here to police the high frequency activity. So those filters reduce the amplitude of fast waves without attenuating slow waves. Attenuating is a really common word in EEG nomenclature, and it means amplitude reduction. The high frequency filter introduces a phase lag. So we have 3 waveforms here, one at 70, one at 35, one at 15. And as you notice, this activity, as I turn the filter down, it shifts the waveform out. And the rule for high frequency filter and low frequency filter is the lower the number, the later the time of the waveform. So this same peak happens much later than at 15 than it did at 70. And the way that I remember that the high frequency filter is a phase lag is if you're high, you lag behind. A lot more fun in person, this joke. So as we look at these two boxes, box A and box B, which displays the effect of the high filter? And it's A, because in A, the lowest number, 15 hertz, has the latest peak. In B, the lowest number, 15 hertz, has the earliest peak. So the answer is A. Lower the number, later the latency, later the peak. The low frequency filter affects low frequency activity, also called then a high pass filter. The low frequency filter introduces a phase lead. Now, one very confusing truth about low frequency, high frequency, low frequency is a lead, high is a lag. But the rule of how it affects data is exactly the same. The lower the number, the later the time of the waveform. So you've got to separate, you've got to know that phase lead is low and phase lag is high, but don't use those terms to try to answer questions like this, because no matter what filter they're talking about, the rule is the same. The lower the number, the later the latency. So in this example, we have the waves in box A and the waves in box B. And in box A, the lowest number, 0.1, has the latest peak. Box A is the graphic that shows the true effects of the low filter. In box B, the lowest number, down here, 0.1, has the earliest peak, and that's not true of the low frequency filter. Now, there are two different settings that control or influence low frequency activity. One is the low frequency filter, and the other is time constant. And time constant, it is defined as the time required for a waveform to fall to 37% of the peak deflection produced when a steady voltage, such as a cow pulse, is applied to the input of the amplifier. So on your test, if you see the number 37%, they're talking about time constant. Now, it's really important, not just for a test situation, but it's also important as you move from lab to lab and work on different equipment that may have low filter, may have time constant. So when we talk about the default setting for low filter is 1 hertz. Default setting for time constant is 0.12 seconds. Now, if I wanted to enhance slow activity on the low filter, I would choose 0.1 hertz. For time constant, it would be 1 second. For low filter, if I wanted to get rid of sweating or pulse, I would use a 5 hertz low filter. For time constant, I would use 0.05 seconds. Now, on any exam, they're not going to show you the frequency response curve, but you have to know what the function of that curve is, and then what does it tell us? So the frequency response curve on the y-axis shows percent amplitude decay. On the x-axis, it shows the frequency of the activity. And then all these slashes through the middle, those are the filter setting. So when we look at this, they're not going to show you a frequency response curve on the exam. However, one thing I want you to notice is if my low filter is set at 0.3 and I have a 3 hertz filter setting, 0.3 activity, 3 hertz filter setting, you will see 70% of the amplitude. You will have attenuation of 30%. So pay attention to those words as you're reading questions. Are they asking you about amplitude or about attenuation? And then at 1 hertz frequency, a 1 hertz filter setting also results in a 70% amplitude present, 30% attenuation. The same is true at 5 and a filter setting of 5. You see 70% amplitude, 30% attenuation. So the main rule to know going into your exam is when the frequency of the EEG activity is the same as the filter setting, you're going to get 70% amplitude, 30% attenuation. The 60 cycle or notch filter reduces waves and frequencies between 58 and 62. The most common cause of 60 cycle is unequal electrode impedances. And again, they're not going to show you this picture on the exam, but I just kind of want to show you what it looks like on the frequency response curve. It's this little notch, and that's why some people refer to it, even equipment manufacturers, as the notch filter. The interpeak interval of a 60 cycle artifact is 16.6. So on any exam, if you see the number 16.6, they are talking about nothing except 60 cycle. So of course, impedances are checked prior to each recording session. Braiding the wires, not literally braiding 3 wires in a braid, but just bringing them all together and taping them together reduces 60 cycle. You must plug your equipment into a secure hospital grade outlet, which is a red outlet. When you have 60 cycle in every channel, the first thing you should do is change your ground. That's typically indicative of a bad ground. So 60 cycle artifact is most often the result of, is it using more than one electrode type? Is it placing headbox cables and power cord in close proximity? Is it putting the EEG equipment near the respirator, or is it high electrode impedances? And although B and C definitely might give you 60 cycle, if your impedances, theoretically, if your impedances are all low and balanced, you should not get 60 cycle. So the answer to this question is D, high electrode impedances. So a couple considerations. When is it appropriate to use the 60 Hertz filter in EEG? Number 1, when it's in all channels. Number 2, after you've changed the ground. The 35 Hertz high filter should be used only for short periods of time. Answer number 1, for short periods of time. Answer number 2, after you have tried to relax the patient. And I had a doctor one time, this is back in the day of paper EEG, when if you peeked around to the back of the EEG machine, there was a pterodactyl on a hamster wheel that actually powered the equipment. But back in the day, I was doing a paper EEG, meaning whatever decisions I made about filter settings, I was stuck with for the interpretation. So I go upstairs, it's a status EEG, rule out status epilepticus on the psych ward. When I arrived to the patient's room, he is being held up against the wall, combative, by 2 nurses. So you and I know a patient that's combative and cussing, and that's not status. Anyway, we were able, in about 4 hours, we were able to get that patient restrained. We were able to get the EEG. But when I turned the EEG on, he was bucking on the bed, and it was just all artifact. Nothing but black ink all over the paper, all over my lab coat. And I turned the 35 Hertz high filter on right away. Again, this is paper. You can't change it back after the fact. So I bring it downstairs to Dr. Greg Damberger. 4 hours. I was smelly. I was just exhausted. He was fighting us the whole way. I said that status EEG from psych is down on the reading board. She comes into the lab. I go in with her because it's just junk. It's just muscle. There's nothing indicative of epileptiform discharges. She opens page 1 and she goes, wow, You went right to the high filter of 35. I said, I know, he was bucking the whole time. She goes to page 2, page 3. She takes a big chunk of paper and goes all the way to the end. And she said, did you have that 35 hertz high filter on the entire time? And I said, I did. And she took that EEG that took me 4 hours to record, and she threw it in the garbage. And I had to go back up there and do it all again. So she knew that patient wasn't in status. She knew that very well. But she had to teach me a lesson that you don't run your EEGs at 35 hertz. And then when is it appropriate to use the 15 hertz high filter? Never, 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 never. That is a never filter. Does it make the EEG pretty? Sure. But you're throwing away the baby with the bathwater. You're throwing away your spikes. You're throwing away your sharp waves. Now, the 5 hertz low filter, or 0.05 per second time constant, can be used in EEG in 3 situations. One, and again, we always try to get rid of the problem by cooling the patient or moving electrodes off of vessels, but we use that 5 hertz low filter when we have pulse artifact, sweat artifact, or it can also be used when you have a focal spike and you want to see that spike better. You can use the 5 hertz low filter for a very short period of time to get rid of the slowing, the after following slow wave after the spike. And then it's appropriate to use the 0.1 or 0.3 hertz low filter to enhance slowing, If you had on a patient 1 gold electrode and 1 silver electrode, what would you see? And here we have gold and AG, AGCL. What would you see? Would you see high impedance readings, 60 cycle artifact, or bias potentials from the differential amplification of the different charge of the metal? And the answer is bias potentials, because each metal has a charge. When you have the difference between activity in 2 electrodes, it's going to amplify not only the brain activity, but also the difference in each electrode metal. For the boards, again, your power cord has 3 wires. If you were to cut the end off your power cord, there's 3 wires in there, a black one, a white one, and a green one. You should know that the black one is 120 volt, the white one is neutral, and the ground is green. I think I didn't get that right on my exam, because first of all, I never felt inclined to cut my power cable. Second of all, I don't know anything about electricity, and I guess red would be the 120 volt one, because it just seemed like if it was something I shouldn't touch, it would be red, but that's not the answer. The answer is black. You should know that capacitance coupling is electrical noise, inductive coupling is magnetic noise, and it is reduced with braiding the electrodes. Of course, the new guideline for long-term monitoring is under 10,000 ohms or 10K ohms and not 5K ohms. There are 2 ways to check the integrity of electrode application. One is impedance testing. That's what's on your EEG machine. You could also use an ohm meter, but it's not advised. When you do an impedance check, a small amount of current goes out to the electrode. And of course, it touches the patient, and then that electricity always wants to return to home, so it comes back to the equipment. And what you're seeing on your screen is the difference in the current that was sent versus what came back. So impedance testing uses alternating current. Now, every time you do an impedance check, it charges the electrode, puts a different charge in the metal. But with alternating current, it charges it and takes it back. It doesn't polarize the electrodes. With resistance testing, that's using an ohm meter, that uses direct current, and that polarizes the electrode. That's bad. Now, back in the day, we used an ohm meter. And back in the day, every Friday, we would take all the electrodes, put it in a big vat of saline, take a car battery, put the 2 poles in there to stabilize the charge on the electrodes. Twice a year, very important question for the exam. Twice a year, you have to get your equipment checked by Biomed. And what they're checking is the chassis leakage current. And in the guidelines, that it states that that leakage current shouldn't be more than 100 microamps RMS with ground open. Now, they might have that number on your exam. They might have it in amps, milliamps, or microamps. So be ready to answer in the unit that they give you. The guidelines say it should be tested twice a year. That might also be listed as biannually or semi-annually. Those are synonymous, twice a year. Not biennially, that's every other year. And it's suggested that the electrodes themselves, which are referred to in the guidelines as patient leads, those should be 10 microamps RMS. You should know your default settings. You should know that a minimum of 20 minutes of EEG recording time, not including activation or calibration, is suggested. There won't be any questions on the test about square wave calibration. And I don't know how many of you still do this, but this has absolutely no utility with digital EEG. Will never be anything but perfect. This square wave calibration was designed for paper EEG. When we would push the EEG machine through the hospital, the screws that held the pens onto the paper would get loose. And we'd have to make sure that they all had the same degree of tightness, that they were all responding the same. Again, not relevant today. I still see neurologists who say, I like that square wave calibration, but it's not necessary. Biocalibration, also not necessary. So to take FP1 to O2 on an analog EEG machine, you're feeding that same input into every amplifier. On a digital system, it's only one amplifier that you're checking. So there'd be no way it would be different channel to channel. So biocalibration, FP1 to O2, not necessary. EEG math. Does anybody's face look like this right now? Because this is how I feel about math. But we're going to go through what you need to know for the EEG exam. So a couple basic tenets that you need to be familiar with is every second of EEG is 1,000 milliseconds. So of course, this is 1 second. The dark lines, of course, are 1 second. Of course, 1 second is 1,000 milliseconds. And then the finer lines are 200 milliseconds. When we talk about defining waveforms, they're defined by the frequency at which they occur, the amplitude in microvolts, and the duration in milliseconds. So in order to do good pattern recognition, which I'm going to say the I word, which no one lets us say as techs, interpretation, you have to be able to interpret EEG to pass the ABRA EEG or CLTM. So pattern identification relies on the ability to identify and calculate frequency, amplitude, and duration. So in order to define, is it a spike? Is it a sharp wave? Spike, the signature of epilepsy, that is defined as an event that it is 20 to 70 milliseconds, sharp wave 70 to 200, and slow wave greater than 200 milliseconds. If a waveform occupies one full 200 millisecond division, it's a slow wave. It would have a duration of 200 milliseconds or 0.2 seconds. To convert from milliseconds to seconds, you take the duration in milliseconds divided by 1,000, and that gives you the duration in seconds. For instance, if you have a 200 millisecond wave, you divide that by 1,000 milliseconds, and that gives you a 0.2 second wave. So when measuring waveforms, you need a metric millimeter ruler, a calculator, and then this look on your this look on your face. So back in the day when we had oral exams, I sometimes saw technicians accidentally using the inch side of the tape measure instead of the meter side of the tape measure. So don't get confused and accidentally use the inch part. These large numbers here are centimeters. The small lines are millimeters. There are 10 millimeters in a centimeter. On any EG or EG exam sample, they will have the display, the paper speed or the screen display. The true paper speed is dependent on the size of the monitor or paper it is printed on. So I want you to ignore all screen settings for these questions. Instead, try to calculate the true paper speed or screen display. Measure, it might say on the screen 30 millimeters per second, but when you actually measure it, it might be less than that. So in this example, this EEG paper speed screen display is 25 millimeters per second. Sometimes the grid lines are not displayed on the EEG. In this case, you find the legend down here, and you measure what that is. So in this case, it's 25 millimeters. So this is 1 second. So you find the legend, measure the legend says it's 25. You can calculate the duration in milliseconds or milliseconds of any waveform by first calculating the number of milliseconds in a single millimeter. So if our paper speed or screen display is 25 millimeters, divide 1,000 milliseconds by that paper speed, and that gives you a display of 25 millimeters per second. So 1,000 milliseconds divided by 25 equals 40 milliseconds in 1 millimeter. So waveform duration is always measured across the base from the point it begins ascending to the time it crosses back to baseline, as you see here. This wave has a 5 millimeter length. If 1 millimeter equals 40 milliseconds that I've calculated beforehand, then 5 millimeters multiplied by 40 milliseconds equals 200 milliseconds. So is this a slow wave, a sharp wave, or a spike? Slow waves are waves that are 200 milliseconds or greater, so it's a slow wave. To calculate amplitude or voltage of the waveform, the sensitivity of the amplifier may be the only indicator displayed on the screen, like 7 microvolts per millimeter. To calculate amplitude, multiply the wave height in millimeters by the sensitivity setting. So if the sensitivity is at 7 and you have a 7 millimeter wave, then your amplitude is 49 microvolts. If no sensitivity is listed, we go again to measure the legend. The legend shows 10 millimeters per 100 microvolts. So if it's 100 divided by 10, that means our sensitivity is at 10 microvolts per millimeter. Now we can measure the height of any wave. This wave is 7 millimeters, and 7 times 10 is 70 microvolts. So when we talk about frequency and duration, all you're doing, if I gave you an example, I said in 1 hour, I want you to jump up and shout your name 4 times. How long do you wait between shouts? So if I said do it 4 times in 60 minutes, you're going to wait 15 minutes. And you're going to use this calculation, time over frequency equals duration. Time, 60 minutes. How often did I want you to do it? 4 times. 60 divided by 4 equals the time in minutes that you're going to wait between each one. So time over frequency equals duration. Time in seconds, 1 second over frequency equals duration in seconds. And we're not going to do these problems today, obviously. In the interest of time, I've given you the formulas, both in seconds and milliseconds, and some more problems for you to work on. Don't feel shy to hit me back with an email regarding these calculations. Thank you for your time today. I hope you're staying safe and staying home. And again, the best email to reach me at is opcal@aol.com. Don't be shy to reach out and ask me for the math answers. And also have a great day. Happy studying.